All right. Okay, now we can get started. Sorry for the delay, and hopefully this works. All right. So on Monday, we introduced numeric methods. We talked about root finding methods, basically ways for us to solve for where a function, some arbitrary function, is equal to 0. And I think we got through quite a few. We had fixed point iteration. We looked at Newton-Raphson method and its closely related method, the secant method. And we ran out of time before we got to bisection method. So let's take a look at bisection method, and we'll also look at a couple other things: derivative approximation, some optimization methods and stuff. Okay, there is something called bisection method, and this is kind of one of the simplest numeric methods for root finding. And the beauty of bisection method is that it almost always works, whereas as far as Newton-Raphson method, it can fail for all sorts of reasons. But bisection method is going to work almost always. Okay, as long as a couple conditions are met, it's going to work. Basically because of some kind of fundamental laws in math, right? And the idea here is we are going to bracket off a root, and we say, well, if we know that a root has to lie within some interval, what we can do is we can kind of keep making that interval smaller and smaller and smaller until we have a sufficiently small zone where we know the root has to be. So all we do is we're going to just say, let's say there is some bracket, some interval, and this says XL, XR. So X on the left-hand side, X on the right-hand side. And if we evaluate the function at X on the left and X on the right, if one side is positive and the other side is negative, and we know it's a continuous function, we know that there has to be a root. Okay, so if you have a continuous function and one side is negative and one side is positive, then there has to be a root somewhere in there. There might be multiple roots, but we know that there has to be at least one root in there. Okay, and so basically, if f on the left-hand side times f on the right-hand side, if the product of those things is less than 0, okay, meaning because that's going to happen if one side is negative and one side is positive, that means they've got opposite signs, and there has to be a root somewhere in there. And so what we're going to do is we are going to take this interval, and we're going to say, okay, we found the left-hand side, the right-hand side, they have opposite signs, and what we'll do is we're going to just chop it in half. We got a midpoint, and we're going to just kind of keep making it smaller and smaller and smaller until the difference between the left-hand side and the right-hand side is close enough together, right? So if we get it to where the left-hand side and the right-hand side are like 10 to the negative 7 apart, and one side is negative and one side is positive, then we know there's a root in between there, and it's got to be, somewhere between. And we're, within 7 decimals of precision there. Okay, so it's very simple. Okay, start with some left-hand side and some right-hand side. Okay, the x on the left has to be less than x on the right, and the signs of x, the function on the left-hand side and the function on the right-hand side, they have to have opposite signs. And if the difference between the left-hand side and the right-hand side is less than whatever tolerance level you specified, so let's say 10 to the negative 7 or whatever, okay, then we'll call it a day. All right. And if it's not, like if you've got a big interval, find the midpoint. Okay, so you're just going to take the average of x on the left, x on the right, and every now and then, it's possible that if f at the midpoint happens to be exactly 0, then we'll stop. Okay, and we'll just say, oh, by coincidence we found this. Now, probability of that is pretty low, but in general, we'll kind of keep going. So what you do is you take that midpoint, and then you say, what's the sign on the midpoint? And so you'll just take the function on the left, multiply it by the function value at the midpoint. And if that's less than 0, then that means the left-hand side and the midpoint have opposite signs, and we will keep the interval going from x on the left to the midpoint. So x on the midpoint will become our new right-hand side. Okay. On the other hand, if x on the left and x at the midpoint have the same signs, then we're going to have something greater than 0. And then that means we're going to keep the other side. We're going to keep from the midpoint to the right-hand side. Because then the midpoint and the right-hand side will have opposite signs, because we know the left and the right have opposite signs. So we'll keep the midpoint to the right-hand side, and we will keep the right-hand side, and we will assign the midpoint to be our new left-hand boundary. And then we just repeat. So we just keep iteratively having our interval until the difference is small enough. Okay. So at every iteration, left and right always contains a root. Assuming we start here, the algorithm is guaranteed to converge, where the approximation error is reduced by a constant factor of 1/2 at every iteration. Okay. So we'll revisit the same function that we've had, log of x minus e to the negative x. And I'm going to just start off with x on the left being 1, x on the right being 2. I'm going to say keep going until we're at the difference between the left and the right is less than 10 to the negative 8. And so I'm going to say f on the left is f evaluated at x on the left-hand side, and f on the right will be f evaluated at x on the right. And we're going to ask, is there a root in between here? We just do function on the left multiplied by function on the right. Is that less than 0? That's true. Okay. And this is basically the algorithm. Okay. So we're going to say if x on the right minus x on the left, as long as that's greater than our tolerance, as long as that's greater than 10 to the negative 8, keep going. Okay. And then we're going to do find the midpoint, left plus right divided by 2, calculate the function at the midpoint. Okay. And we're going to say if f at the midpoint is 0, then and if that's true, then we'll break. Okay. I've got identical all dot equal f at the midpoint 0. Okay. So this is just kind of like if this is close enough to 0, because again, you might not get exactly 0, but if it's within machine square root of machine epsilon, then it will do that. And the reason why I have to do this identical is all equal identical to true is because the default behavior of all equal, which is a little frustrating, is rather than doing true or false, it's true, and if it's not true, it spits out a string that says mean error, mean relative error, something like this. And that's annoying. And if you do if mean relative error something, it gets coerced into a logical value, and so it's frustrating. So anyway, you say, is that thing identical to true? And that's going to come back false. So anyway, okay. So as this rarely gets invoked, but otherwise we'll do this. If f on the left times f on the at the midpoint is less than 0, then we're going to take the midpoint and assign it to xr. And if not, we will take the midpoint and assign it to x on the left. Okay, we haven't reassigned anything, xr, xl, and we will just increment our iterations by 1. Okay, and that's it. Okay, so we need fl and fr calculated and accessible to us in the global environment. This is not a function; it's just a while loop that's running inside the global environment, and that's fine. And then and we will at the end we're just going to ask what's the difference between x on the what's the midpoint of x on the left and x on the right. Okay, and so when we let this run and we get 1.3098, which I don't know, maybe looks familiar to us because we saw it a lot of times on Monday because that was the solution, the root to this function, and it took us 24 iterations to get there. To illustrate, this is kind of what it looks like. We started off with x on the left being 1, x on the right being 2, here's my midpoint at 1.5. We can see this has negative and this side is positive. So we're going to throw away the right-hand side. Okay, and then, so at the next iteration, we find the midpoint here, and we will end up throwing away the left-hand side. So this is now my interval, 1.25 to 1.5. And then I'm going to find the midpoint here, and I think it's like right here, and we end up throwing away this side. Okay, and then so now I divide this by 2. Okay, and it's a little hard to see, but when you do this, the midpoint isn't exactly 0. It's very close to 0, but it's not within machine error. So we'll throw away the right-hand side, and then we have this on the left. Okay, so then I divide that by 2, I divide that by 2, and I just kind of keep going and going and going until we zero in. This interval gets smaller and smaller and smaller. Okay, each time the width of my interval goes down by a factor of 2. Okay, and that's bisection method. And I think I put this in as an extra credit problem in your homework. So in your homework, you have to do all of these methods, and you can try this out. Question? Yeah. Like if we have, yeah. So okay. So I don't have do I have a way to draw this? Yeah. So if you have multiple roots, okay. So let's say you have something like this, right? So I've got multiple roots here, right? And if my left-hand side, this is x on the left, I got x on the right, right? So this is positive, and this is negative, okay? And all I'm going to do is I'm going to just, it's just guaranteed to find one of the roots, okay? So I'm going to like go to the midpoint here, okay? And as far as the thing is concerned, and maybe I should try to get this in the picture here. I don't know how this is going to work, okay? So if this is x at the midpoint, okay, as far as this is concerned, it's just going to say this is negative, and it's not going to bother. It's just going to throw this away. So there are technically 2 roots here, and it's just going to throw that side away, okay? And then it'll say, okay, here I've got a negative, here I've got a positive. There's got to be a root somewhere in here. I find the midpoint. I'm going to say, okay, and then it's going to throw this side away. And then, all right, this is negative, this is positive. It's going to throw this side away, and so on and so forth. Okay. What it will have trouble finding, it's going to have trouble finding roots where. Sorry, I know I could just use another part of the screen, but because I'm like, I don't even know if it's even visible in the video. If you have something like, or just, so this is technically a root here, where it just kind of kisses that there, okay? The method probably won't ever find this one, okay? So I've got x on the left, x on the right, and you do the midpoint, and it's going to say, okay, x on the right is positive, x at the midpoint is positive, and it's going to keep this side, and it'll find this root eventually. Okay, but over here, there's never going to be a situation where you have x on the left and x on the right having opposite signs. Okay, and so bisection method doesn't work for this. But as long as you've got, and if you have, so you might have multiple roots between some interval. It'll just find one of them. Okay, it's guaranteed to find at least one of them, where it's if it crosses from negative to positive. But yeah. So yes, technically you can have an interval where it's positive to positive, and there's a root inside there, but bisection method is not equipped to.
Like a parabola points like in the middle, so like there is like a positive and negative for both sides, which
No. Well, that won't be. So the question was, what if? Okay, so this would not be a valid starting interval if it was like this. This is not a valid starting interval because x on the left is negative, x on the right is negative. This you would not be allowed to start with this interval. Okay, so you're starting. The rules for starting has to be x on the left has to be x on the left and x on the right have to have opposite signs. So you can't have a situation where, you have this parabola, you got two roots in there, and you're on negative on the left-hand side, negative on the right-hand side. So, yeah, you gotta kind of do this. Okay. Best of both worlds. Always be wary if somebody says claims best of both worlds, but anyway. So root finding can be tricky and it can fail for all sorts of reasons. And bisection method is like guaranteed to work as long as you start with one negative side and one positive side. It's guaranteed to work there, but it's slow. Okay, right? You're dividing it in half, which seems pretty good, but it's like you're just dividing by half. So a lot of times, what we do is we start off with bisection method, okay? And then we get to say, I don't know, 10 to the negative 2 or 10 to the negative 3. And it only takes a few iterations to get to within 10 to the negative 2 or 10 to the negative 3 of some place. And then we can switch over to Newton-Raphson, okay? And we can say it for, at Newton-Raphson here, we're close enough to the root so that it's going to just kind of converge very, very, very quickly to the thing. Okay, let's see. Let me give you your first view quiz answer for today, which is, wait, I haven't given you anything, right? Okay, today's first one is C. C as in cat. C as in cat. Okay, so all right, if we want to talk about order of convergence, we've got some root and we've got some approximation xn, okay, be the nth approximation, so that is your approximation after n iterations, okay, then the error at the nth iteration, your nth error is going to be e sub n. And we can figure out kind of an order of convergence to have some, basically some value here, right? And we can say if we're multiplying, it's basically e to the n raised to some power is going to be the next value here, okay? So if it's shrinking at a very high rate, okay, where we can increase power to p is like, 2, 3 or something, okay? And on the other hand, maybe it's the next iteration is only a, some smaller power version of this, okay? So for example, bisection method, it's linear convergence, okay? The order of convergence is just 1 because the next iteration is just your current error divided by 2, okay? So we're not raising whatever our current error is to some kind of power. We're just multiplying it by 1/2. So it's linear convergence. We are shrinking our error every iteration, but it's not something raised to some power, okay? We're not going to bother with the math behind this, but Newton-Raphson method has quadratic convergence, which is pretty fast, okay? Secant method has convergence ratio, order of convergence of 1.6, okay, which is not as fast as Newton-Raphson, but it's still pretty good, okay? Golden ratio, order of convergence. All right, so we're just kind of comparing these, which one's faster. Okay, let's take a small detour, I guess, and we'll talk about, numeric methods for approximating other things, like approximating a derivative. And this could be useful if you wanted to do something like Newton-Raphson Method, but you're struggling to find the derivative. So in Newton-Raphson Method, you've got to find the derivative in order to get the value at the next iteration. So you take your, f at xn and the derivative of f at xn. Right? And we said this is how we do Newton-Raphson Method. Okay. And if we're able to figure out the derivative, that's great. Okay. So in the example that we've been doing, we have log x and e to the negative x, and we said, okay, let's take the derivative of this. Derivative of log x is 1 over x, and derivative of e to the negative x is e to the negative x times -1. So with the chain rule, it becomes plus. And that works. Okay, that works. We can find f at some function, or some value 5. We can find the derivative at that value 5. Okay, and so the derivative at 5 is 0.2067379. Okay, and that's fine, right? So this is the function. Here's our tangent line, and we can draw the tangent line, and that's the slope of the tangent line is that. Okay. What do we do? What do we do when we're in a situation where maybe we have trouble finding the derivative? Okay, and in these situations, we can approximate the derivative numerically. Okay, and all we're going to do is we're going to just kind of use the definition of a derivative, but rather than taking the limit as h goes to 0, we're just going to use a small value of h. Okay, so the derivative, the formal definition of a derivative is, you take the value of some function at some location a, and then you take the value of the function at a plus some tiny value h, right? And you say, well, how much did the function change? Right? That's going to be the numerator. How much did the value of the function change? And then you say, okay, well, how much did the value of the function change versus how wide is that little delta, that little h that you've added? And we say, well, as h goes to 0, that's going to be the derivative here. And all we're going to do is we're going to just say, well, we won't plug in 0, but we'll plug in like 10 to the negative 6 or something like that. And we'll just have the computer approximate the derivative by plugging in a suitably small h. Okay, so here I'm going to say, all right, let h be 10 to the negative 6. Here's my function. Okay, and we're going to say, let's plug in x. We'll plug in x into log x minus e to the negative x. And then we will do x plus h, and we'll do what's log of x plus h minus e to the negative x plus h. All right, and we say, okay, well, here's f of x plus h minus f of x, and we'll divide by h. Okay. And so this is my approximation of f prime. So if I say print it out to 12 digits, what is the approximate value of f prime? At 5, I get 0.2067379. And then when I did the actual value of f prime, the quote, again, this is an approximation still because of floating point limitation, but here we're plugging the actual thing, 1 over x plus e to the negative x, okay? And so when we did that, we can see these two things align up to what? 1, 2, 3, 4, 5, 6, 7 decimal places. And it's just these last few digits, 1, 2, 3, 4, 5, these last 5 digits are different, okay? So we're accurate up to 7 decimal places, and it's only at the 8th decimal place do we get some kind of difference. And so probably for most intents and purposes, this is good enough, okay? This is going to be good enough for our cases. And this didn't involve us doing any kind of analytic solving of the derivative. Okay. Now, we can calculate the derivative from the left-hand side or the right-hand side, right? So here I added a positive h, and what I can do is I can also just say, whoops, add a negative h. Okay, so rather than going from 5 plus 10 to the negative 6, I can do 5 minus 10 to the negative 6 and see how much it changed there. Okay, and so same exact thing. I'm just adding a negative 10 to the negative 6. And if I do that, I get I get something very, very, very close, okay? So the true value is this, 20673794699. Okay, that's at least up to 12 digits. And if I take the left-hand side approximation, the last few digits are 70299, so just a tiny bit higher than 4699. And the right-hand side approximation is 23699, okay? The right-hand side approximation is just a tiny bit too small. And what's going on is, if you look at this curve, and again, what I've done is I've exaggerated what's going on, is the true curve looks something like this. And here's our thing, and this is the true tangent line, okay? And if you do x, so this is x, and if I go plus h, I end up over here, okay? And so this is highly, highly, highly exaggerated. So x plus h, my slope is a little too shallow, okay? And over here, if I do x minus h, down to over here, x minus h, this is lower, and so my slope ends up being a tiny bit more positive, okay? And that's if I have the curvature, what is this, concave down, okay? If you had concave up curvature, you would have the opposite problem. The right-hand side derivative would be too large, and the left-hand side derivative would be too negative, right? Or not too negative, but too not steep enough, right? Not big enough. So so that could happen, okay? So anyway, again, this is highly exaggerated, okay? But because of the curvature, our derivatives are a little bit off. So what we can do is we can just average the right-hand side and the left-hand side derivatives. So if I have some h, I can do f of x on the right-hand side and f of x on the left-hand side, and I do x plus h versus x minus h, calculate the thing, and I'll take the difference between f of x plus and f of x minus, and I'm going to divide by 2h. And if I do that, then my approximation is accurate up to 10 digits. 20673794698 and 946999, right? So now this thing is accurate up to 10 decimal places, which by default R only prints out what, 7 or 8 decimal places, or I don't know what the default options are, but this is pretty good, okay? So that's derivative approximation. We're just adding on tiny little increments and calculating basically the change in the function divided by the size of your increment. Okay, and so here I've been plugging it into log of x minus e to the negative x, but we can pass functions themselves as arguments into another function, right? So here is a function, and this is going to be some derivative approximation here, and it will accept as one of its arguments some function, the location x, and some default delta h, okay, default change h here. And here we're going to just say, on the left-hand side, we're going to do x minus h. On the right-hand side, we're going to do x plus h. Calculate f on the right-hand side minus f on the left-hand side. Okay, function at the left-hand side, function at the right-hand side. Take the difference between those things, divide by 2h. Okay, and again, we're just going to pass in whatever function we have. So just some arbitrary function, and this is it. This will give us an approximation to the derivative. We don't actually have to analytically calculate the derivative at all. We just estimate this by doing this. Okay, and so here is my function f, log of x minus e to the negative x, and here I'm going to just plug in f into f of the derivative, right? So we're going to plug this in, and we're going to say calculate this, and I get this is my approximation 0.267376984, okay? And we can say, all right, what if I have another function, x squared, okay? The derivative of x squared is really easy. It's just 2x. And I can just say, okay, what is the derivative of our function, f2, our x squared function at 5? And it says it's 10, and it looks like it's working, okay? Now, if we say, what is the derivative, if we see print 12 digits, we can say, okay, it's not exactly 2x. It's 10.00000000014, so it's off at the 9th decimal place. It's accurate up to 8 decimal places, and at the 9th decimal place, it's off. So it's a tiny bit off, but I think it's pretty good. Nobody had to do any math to figure this out. I can plug in other things, sine of x, cosine of x, whatever, and we're going to get pretty good approximations here. All right, so that's kind of cool. And what we can do is we can specify different values of h, and we can see how things get thrown off. So here I'm going to just say digits equal 16. And let's just see, what if my h is 10 to the negative 5? What if h is 10 to the negative 6? What if h is 10 to the negative 7? What if h is 10 to the negative 8? Okay, and we see actually our derivatives get a little bit, at 10 to the negative 6 we get pretty good. At 10 to the negative 7, the approximation is actually more off, right? So this is accurate, at 10 to the negative 6, I'm accurate to 1, 2, 3, 4, 5, 6, 7, 8 decimal places. At 10 to the negative 7, I'm hitting 1, 2, 3, 4, 5, 6, 7 decimal places of precision. And at 10 to the negative 8, I'm 1, 2, 3, 4, 5, 6, 7 decimal places of precision. But here I'm off, in the 8th decimal place, I'm off by around 3. Here in the 8th decimal place, I'm off by around 6. And over here, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm accurate up to 9, and I don't know. Okay, so we can see the amount we're off actually doesn't necessarily get smaller when my h gets smaller, okay? So you might think, well, we want to take h as close to 0 as possible, but what's going on? As I make my h even smaller, the amount of error is actually getting bigger. What do you guys think is the problem? Yeah, we're running into the limitations of kind of floating point arithmetic, okay? So at floating point arithmetic, we got 52 bits. We can only accurately represent maybe 16 decimal places of precision. And so when we do something like 10 to the negative 7 or 10 to the negative 8, we're running into kind of this issue of catastrophic cancellation, where the value themselves is just a little bit off from the real thing. But when you're trying to calculate the difference between two things, because the relative difference is so small, it gets kind of wiped out, right? And so we're running into basically the precision limits of floating point arithmetic, and therefore a smaller h is not always necessarily better. And it's going to change. What h you should use will change based on your function. So if you're taking something up to like the 10th power, okay, then your h might need to actually be quite a bit bigger, okay? And so here we can see, even as it gets even more extreme, 10 to the negative 10, 10 to the negative 12, 10 to the negative 14, 10 to the negative 16, we're off by quite a bit, right? The true derivative being 10, and we're off by 8.88, and that's because, that's 10 to the negative 15. And if I try to do 10 to the negative 16, I've really hit the limit of floating point accuracy, right? Because we can really only show up to 16 decimal places of precision. And so here, if I try to do this, it can't even register the difference. And it says that your derivative is 0, because the difference between 10.0 or 5.0 and 5 plus 10 to the negative 16 squared, the difference there, that just registers as 0. So we can see the accuracy drop dramatically, and calculation actually returns 0 here. Okay, let me give you your second view quiz answer. Second view quiz answer today is B. B as in bear. B as in bear. And okay, let's talk about numeric optimization. So we've been talking about root finding this entire time, and we can apply this to help us find local minimums and local maximums. Yeah, question?
I wanted to ask if the choice of H also depends on how large the X you're calculating.
Yes, absolutely. How large your X is that you're calculating, right? So if you wanted to find the derivative at X equals, say, 1 million, okay, then your H will have to be comparably much larger. Because again, with X equal to 1 million, you know, that 52nd bit is now, you know, probably, I don't know, 10 to the negative, I don't know, something else, right? 10 to the negative 10 or something, right? And so your H will probably have to be a lot bigger, at like 10 to the negative 2 or 10 to the negative 3, something like that. So yes, absolutely. Wherever that X is that you're calculating the derivative for will influence what size H to use. Okay, so all of these root finding methods, we can kind of turn into optimization methods. Optimization methods is all about finding a local minimum or a local maximum, okay? You know, a lot of times we want to find the global minimum and the global maximum, but finding a global minimum or global maximum is actually quite hard. So we're going to just say, let's find local minimums and local maximums. And just from calculus, you learned you can find a local min or local max, or at least possible locations of local mins and local maxes by finding where the derivative is equal to 0, right? You find where the derivative of a function is equal to 0. That should be a place to check where you might have a local min or local max. Could be a saddle point, but that's what we're going to do. So basically, we have derivative-based optimization, and so if we wanted to find a local min or local max, step 1, find the derivative of f, and then step 2, applying a root finding method to the derivative. Okay, you find the roots of your derivative, and then you can now evaluate those critical points to figure out if you got a local min or local max, and that's it. That's it. Okay, so but everything we can just use numeric approximation methods. So step 1 is find the derivative, but you don't actually have to analytically find the derivative. You can just say, hey, let's use the derivative approximation function, and let's try to figure out where the derivative approximation function is equal to 0. And that's going to give you something close enough to the true critical values or critical points. Okay? Or, you know, if you wanted to just do it for Newton-Raphson, okay? And let's say you are able to find the derivative analytically, and you're able to find the second derivative analytically, okay? The Newton-Raphson method is super great. All you have to do is your next iteration, rather than doing f divided by f prime, your next iteration will be f prime divided by f double prime, okay? Take your slope divided by the second derivative, and for this to work, your function needs to be twice differentiable, and now the second derivative cannot be 0 in any of the sequences, okay? In any of the locations that we're checking in our sequence exit time in. So let's say we wanted to find local mins, local maxes of this thing, okay? And so analytically, we can find the first derivative. Analytically, we can find the second derivative easily, and we'll just apply it, okay? Find the roots of this thing by, we can find the roots of f prime. And so here's the function, x to the 4th minus 0.5x squared. This is what the function looks like. And if I start at, say, 2.1, it's going to find a critical value at 1. And if we go look here, we can see, oh yeah, 1 corresponds to a local minimum. If I start at 0.9, and I just, say the next iteration is going to be f prime divided by f double prime. Also, it takes me to 1. It's going to say that's a critical value. Okay, so all of these things, I'm just updating the next value as doing x old minus f prime of x old divided by f double prime. Okay. Here, if I start off at 0.1, I get a critical value at basically 0. And we can see, oh yeah, that corresponds to a local max. If I start at -10, it identifies the critical value at -1. Okay, so just like all of these other methods, your starting location has a heavy influence. So Newton-Raphson method, your starting location will have heavy influence in terms of which root it's going to find, and likewise, your starting location here is going to influence which critical point it's going to find. But here it's just finding where the derivative is equal to 0, and where the derivative equals to 0 is going to correspond to some local min or local max. And all of these things, we've just been, this is applying Newton-Raphson, but we could do, say, bisection method to the derivative. And again, with if you look at how we ran the bisection method, going back here, okay, all we're doing is we're just plugging in some function here, okay? And so this function here could just be the derivative approximation function as well. We can just say, hey, what's the derivative approximation at this point? And so whatever it is, you can just plug in some function. As long as it's spitting out a value, you can run it in here. Okay, let me go ahead and give you your last view quiz answer for today. Today's last view quiz answer is A. A as an apple. A as an apple. And that'll be your last view quiz answer. Okay, we'll wrap it up here for now. Have a good rest of your day. I think I posted homework 5. All right, so that's up. I know you guys are still wrapping up homework 4, but homework 5 is online now, and you can take a look, and it takes, as you work with ggplot and these root finding methods. Okay, we'll see you all on Friday. Have a good rest of your day.